Hello, this is Jennifer Martinez. In this video, we're going to look at applications of linear systems. The example we're going to look at is called the exchange model, and it was created by Leontief. And in another section, we're also going to look at another model created by Leontief called the production model, or sometimes known as the input-output model. So because of this, I would like to read the introduction of this chapter that's in the book on a history of Leontief. So it says here that it was late summer in 1949, and Harvard professor Wassily Leontief was careful feeding the last of his punch cards into the university's Mark II computer. Believe it or not, one of my first computer programming classes used punch cards to be able to write our programs. So continuing, these cards contain information about the U.S. economy and represented a summary of more than 250,000 pieces of information produced by the U.S. Bureau of Labor Statistics, and after 2 years of extensive work. Leontief had divided the U.S. economy into 500 sectors, such as the coal industry, the automotive industry, the communications, and so on. For each sector, he had written a linear equation that described how the sector distributed its output to the other sectors of the economy. Because the Mark II, one of the largest computers of a day, but still could not handle the resulting system of 500 equations and 500 unknowns, Leontief had distilled the problem into a system of 42 equations and 42 unknowns. And if you read the next paragraph here, you'll see that it took the computer 56 hours before it finally produced a solution. Leontief, who was awarded the 1973 Nobel Prize, by the way, opened the door to a new era in mathematical modeling in economics. His efforts at Harvard in 1949 marked one of the first significant uses of computers to analyze what was then a large-scale mathematical model. Since that time, researchers in many other fields have employed computers to analyze mathematical models. Because of this massive amounts of data involved, the models are usually linear. That is, they are described by systems of linear equations. The importance of linear algebra for applications has risen in direct proportion to the increase of computing power, with each new generation of hardware and software triggering a demand for even greater capabilities. I really like this this introduction, not only because it shows the importance of linear algebra and the connection with linear algebra and computer science, it also is an introduction to our first example that we're going to do in economics. Which brings us to our next paragraph. Suppose a nation's economy is divided into many sectors, such as various manufacturing, communication, entertainment, and service industries. Suppose that for each sector, we know the total output for 1 year, and we know exactly how this output is divided or exchanged. We're going to first do the exchange model among the other sectors of the economy. Let the total dollar value of a sector's output be called the price of that output. Leontief proved the following result. He proved there exist equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances its expenses. Doing this, you will have a smooth system, a well-running system. So let's look at example 1. So the following example shows how to find those equilibrium prices. So example 1. Suppose an economy consists of coal, electric, and steel sectors. So we're just going to use 3 sectors to keep it simple. And the output of each sector is distributed among the various sectors as shown in table 1, where the entries in a column represents the fractional parts of the sector's total output. So these are outputs. And we're going to denote the prices in dollar value of the total annual outputs of coal electric, and steel sectors by PC, PE, and PS respectively. If possible, find equilibrium prices that make each sector's income match its expenditures, so we have the smooth running system. So the first thing I'm going to do is let P sub C be the price of the total annual output of the coal sector, and PE be the price of the electric sector, that total annual output, and PS, the steel sector. To explain what this table means, I'm going to start with this middle column here, the electric sector, and I realize 0.4 is purchased by coal. So on the left here, I have 3 pictures of the 3 sectors. So I'm going to say that electric, the output of electric was purchased by coal, and 40% of it purchased by coal. I'm going to skip electric to electric and go to the 0.5. 0.5 of the electric was purchased by steel. So that means 50% is the output of steel. That 0.1, what that means is 10% remains then with electric. Notice how these add up to 100% and these columns add up to 1. Let's do the same thing for coal now. Coal, 0.6 goes to electric, so 60% goes to electric, and 40% goes to steel. It doesn't keep anything. That automatically adds to 100%. And finally, steel. 60% goes to coal, 20% to electric, and it retains steel to steel, 20%. So this is what this means. So you can see that at the end, we want a equilibrium price. What make this all flow in a nice continual way. So now what we're going to do is we're going to look at the horizontal. The horizontal are going to be the inputs. So if you can see here, purchase by coal is 40% of electric and 60% steel. You could check out, those are the inputs here of coal. So coal spends 40% of the price of electric, where that's the total annual output, plus 60% of that price of steel, or PC is going to equal to 0.4 PE plus 0.6 PS. And again, we want this expenditure so everything flows nicely. We can do the same thing with the second row, right? The price of electric. Electric spends 6% of PC plus 10% of PE plus 20% of PS. And again, PE, yes, I realized 10% on itself. So that would be 0.6 PC plus 0.10 PE plus 0.20 PS is equal to the PE. And the same thing for the third. PS equals 0.4 of PC plus 0.5 of PE plus 0.2 of PS. So we have 3 equations and 3 unknowns. And I'm going to write this in order. PC first, PC, then I'm going to subtract that 0.4 PE minus the 0.6 PS. Notice this is a homogeneous equation, that all 3 are going to be homogeneous since every single term there has a variable. The next one is PC first, so I'm going to do negative 0.6 PC. Then PE, and if I subtract the PE, 1 minus the 0.10 would be 0.9 PE. And then now PS, subtract that over, minus 0.2 PS, again equals 0. And the last one would be negative 0.4 PC, negative 0.5 PE, subtracting this over, plus 0.8 PS equals 0. So let's write this as an augmented matrix. And now I'm going to solve this. You could do this by hand, but since this has so many decimals, I'm going to go ahead and do it on my calculator. So to do this on your calculator, what you're going to do is go to second matrix. and you need to type in your metrics. So you need to go to edit. So go over to edit. Now I've already typed it in. It's a 3x4 matrix, so you just change that to a 3x4. And how you do this, just do it 3, enter 4, and then it takes you straight to your matrix, and then you just type these in. Just keep on typing enter, and it'll bring you to all of these, right? 1, enter, you get to the next one, and so forth. It goes across. So once you type it in, what you're going to do is go to second quit. You got to get out of this. It's real important. Otherwise, you're going to put your math right in there. So you go to second quit, and then you're going to go back to second matrix. This time you're going to go to math. So you go 1 over. And what you're going to do is look for reduce row echelon form. If you go up, good to it quicker. There it is, RREF, reduce row echelon form. So this is just row echelon form. B is what we want. So I'm just going to press enter. And then of what? So of matrix A. So you go back to matrix for the third time. And this time I'm going to go keep on names and just press 1 for my matrix. Press enter and you have it. There it is. So let's move that over to the screen. And I rewrote it here. I decided to round to 2 decimal places. This is PC, PE, and PS is what that means. So now we can find the general solution. So we know that PC minus 0.94 PS equals 0. So then we get our first equation. Our second equation, we can do the same thing. And we know that P3 is free. You could also write it in parametric form. That's what I did here. P is equal to PC, PE, PS. So that's what PC, PE, and PS is. I factored out a PS, and this is it. So this is called our price equilibrium vector, which means for any non-negative choices for PS, we can find the prices for each sector since PS is free. For example, if PS is 100, that is, if you remember what PS was, the price of the total annual income of the still vector, then we can find the total annual outputs of the coal vector. That would be, you would multiply it here and get $94, and then the price of the electric sector, which would be 85. That's supposed to be an 85. These would be the 2 prices that you would need if the PS is 100 to make our system run smoothly, the equilibrium vector. The last thing I would like to do is look at this practice problem to create just the table. So it says here, suppose an economy has 3 sectors, agriculture, mining, and manufacturing. So what I did here is I made pictures of the 3 vectors. Agriculture sells 5% of its output to mining. So I made an output to mining, 30% to manufacturing, and retains the rest. So that means 35% is spent on mining and manufacturing. If it retains the rest, if I add up to 100, that would be 65% up here. So now let's look at mining. 20% to agriculture, 70% to manufacturing, and it retains the rest, so that's 90%, so 10% to itself. Finally, manufacturing is in light blue. 20% of that outcome goes to agriculture, 30% goes to mining, and that would be 50% it retains. So we're going to determine the exchange table for this economy, where the columns describe how the outputs of each vector is exchanged among the 3 sectors. So this is a practice problem, so we can just look at the solution. You're going to write the percentages as decimals. Since all the outputs must be taken into account, make sure that the columns sum up to 1. You can see the orange, agriculture to agriculture, 0.65, to mining, 0.05, to manufacturing, 0.30. The second column, that's going to be the mining, which are in green, and then finally manufacturing, which are in blue. And again, they all add up to 1.